Here are your solutions to Lesson 7 in Chapter 4. Lesson 7 is linear and nonlinear functions. So some of the problems that we're going to be looking at will be linear functions, some of them will be nonlinear functions. So the first thing we want to do is take a look at our box here when we're talking about identifying linear versus nonlinear functions. In a previous lesson you learned that linear functions have graphs that are straight lines. So if it's linear, think about it, it has the word line right in it. Those are straight lines. So if you can graph a function and it's a straight line, you can immediately determine that that is a linear function. To finish this now, this is because the rate of change between any two data points is constant. So a constant rate of change creates that straight line or that linear function. Now, a new vocabulary word starting today is nonlinear function. Nonlinear functions are functions whose rate of change are not constant, therefore their graphs are not straight lines. So, for example, you might end up with a graph that looks like this, which is a very common nonlinear function. Please put this in your vocabulary and, if necessary, on your gold sheet. So let's take a look at problem number 1 here. It asks us to determine whether each table represents a linear or a nonlinear function, and then explain that. So basically what we're looking for is if it has a constant rate of change, we're going to say it's linear. If it's not constant, we're going to say it's nonlinear. And there are two ways to figure that out, which you're very familiar with. First of all, you can do exactly like they did here in the chart, and you can recognize that the change from 2 to 4 is plus 2, from 4 to 6 is plus 2, etc. And then you can move over here and you can say in order to get from 50 to 35, I would have to subtract 15. From 35 down to 20 would be subtract 15, and you can check. If you want to prove that it's linear, you need to check each individual cell to make sure that it stays linear. Okay? So, in other words, after looking at this, we can recognize that as x increases by 2, y increases by 15, and it's each time. This is very important. Therefore, we have a constant rate of change, so we can say it's linear. I would like to point out something else here that they don't necessarily show, and that's we can think of this as what would I have to do with 2 in order to get 50? With an input of 2, how would I get an output of 50? And you could say, okay, I'm going to multiply by 25. And then then you would look at this and you say, what would I multiply? So if I multiply 4 times 25, will I get 35? And the answer is obviously no. So in some cases, recognizing that we can multiply the x value by some constant in order to get the y value leads us to an easy conclusion that it's linear or not, but in this case that doesn't work. So that's why I want you to make sure that you recognize that this is probably the quickest, easiest way to figure out whether or not we have a linear function, if the rate of change between x and y is constant. Alright, so let's take a look at problem number 2. It asks us to do the same thing. So the first thing we do is check our change in our x values, and as you can see here, it's already written here for you, we keep adding 3. But in this case, from 1 to 16 is a plus 15, but 16 to 49 is a plus 33. And then we go up to a plus 51. So in other words, the rate of change is increasing from cell to cell. So we do not have a constant rate of change. One thing I want you to make sure of is when you're looking for rates of change, make sure you compare this value to this value, because like you can see right here, we're not moving up by 1. If the x values, the input values, increase by 1 in each case, it makes it easier to look at this. So be careful when they're not increasing by 1 that you really look at it closely and understand what you're looking at. But in this case, it's pretty straightforward. We do not have a constant rate of change, therefore we would say no or non-linear. It also says, or it also shows us that another way to look at this is we could graph this. So our conclusion would be as x increases by 3, y increases by a greater amount each time. Therefore, it is nonlinear. And another way to look at this is to put it in a graph. And remember, you could create a table in a graphing calculator, and if you'd like help with that, I'd be happy to. Put it in a graphing calculator, and the graphing calculator would graph this for you, and this is what the graph would look like. And you would see that you have a nice curve here, It is clearly not a line, and therefore it is not non-linear. Please press pause and do letters A and B. All right, let's take a look at problem number 3. It asks us to use the table right here to determine whether the minimum number of calories, this is calories here, a tiger cub should eat is a linear function of its age in weeks. So if we input its age in weeks, we will find how many calories we need in order for that tiger cub to progress normally. So at 1 week, it needs 825 calories. At 2 weeks, it needs 1,000 calories. At 3 weeks, it needs 1,185 calories, etc. So the first thing we want to do is find out, is this a linear function? So we can look at this right away and see that we are +1 in each of these. Pretty easy to do that math in our head right away. From 825 all the way up to 1,000, well, from 825 to 900 would be 75, and another 100 up to 1,000 would be a +175 here. And then if we take a look at this cell, it's easy also to do the math in our head. That's a +185 from 1,000 up to 1,185. That's easy. And we could see right away that this is a case of no, this is nonlinear. So you can write nonlinear. The rates of change are not the same. It is nonlinear. Now it says to check it, you could graph it. 4 we can see is at 1,320, which would be about here, and 5 would be at 1,420, which is going to be just over 1,400. So you can look at this and you can see, and it's not really easy to tell on this, but you should do this either in a graphing calculator or on graphing paper, and you would see that this is not a straight line. Because at first our change is 175, then it goes up to 185, and by the time we get here it's down to a change of 100. So in other words, it would be rising faster here and then tapering off here and becoming less and less of a change, and we definitely do not have a straight line. Please press pause and do letter C. Okay, let's move on to problem number 4. A square has a side length of s inches. So whenever we talk about a square, we always talk about the side length is s because it's s times s to get the area, or we can say that area equals s squared. The area of the square is a function of the side length. In other words, the amount of area we have depends on how long a side length is. Does this such situation represent a linear or nonlinear function? And then they want you to explain that. Well, we could make a table of values. We could put an input of 1 for a side length, and 1 squared is 1, so we would get an output of 1. Put an input of 2 in, and 2 squared is 4, we get an output of 4. We could go way out here to 10, and we would easily see that the area would be 100 because 10 squared equals 100. So we're going to say that we've got +1 in every case here, but if we look at the values here, we can quickly see that they are not rising by the same amount. We have a +3 to start out with. By the time we get way out here, we are adding 9 each time. So the first thing we can immediately say is that clearly it is a nonlinear function. So this is nonlinear. Another thing we can do is we can check this in a graph, and this would be a great situation where we could easily use a graphing calculator to check this, and I hope that you will take the time to get a graphing calculator and go and look at this, because think about this. What is our equation here? Our equation is area equals s squared. Well, we can put that in a graphing calculator really easily by saying that area is our output, which in a graphing calculator is y, and our input is the side length, so we can just put y equals x squared in a graphing calculator, graph it, and it will look like this right here. We will start out with a slow rate of change, and it will become greater and greater and greater and keep turning to the point where it becomes almost a straight line, straight up and down. Clearly not a linear function because it is clearly not even close to a straight line. This would be what a straight line would look like versus what we have here. Please press pause and do letter D.